So I think we start. So hello, good morning. I welcome you to the next talk in the European edition of the One World Signal Processing Seminars. Today we are featuring a talk of Professor Felix Krahmer from Technical University of Munich. He will speak on unlimited sampling from theory to practice. I remind you to mute your microphones, and if you have questions, type them into the chat. We will collect them and address them at the end of the talk, and then you also have the chance to ask further questions. I would like to introduce Professor Felix Krahmer. Felix Krahmer studied mathematics at the International University Bremen, which is today Jacobs University, the Université de Paris Sud, and New York University's Courant Institute, where he acquired his doctoral degree. He was a postdoctoral researcher at the Hausdorff Center for Mathematics in Bonn, and from 2012 to 2015, junior professor and head of an Eminöter junior research group at the University of Göttingen. He joined TU Munich in 2015 as an assistant professor, and his research focus lies on the mathematical foundations of signal and image processing. This covers randomized sensing methods, especially in compressed sensing, dimension reduction, and analog to digital conversion. His research not only involves theoretical analysis, but also the applications. Having said that, it comes at no surprise that his talk today is entitled Unlimited Sampling from Theory to Practice. I would like to welcome you here, Professor Krahmer, to speak at the One World Signal Processing Seminars. Yes. The floor is yours.
Thank you very much. Thank you very much in particular for this very kind introduction. I'm very happy to be here and give this talk in front of this truly international audience. So I just realized that I have now put here on the slide sensing and sampling, so we use both of them in a slightly different context. So I guess what I will tell you is sort of touching on sampling for sensing. So it's that's why both make sense. I should mention what I'm presenting to you today will be joint work with a number of co-authors. In particular, my key co-author on this line of works, who's Ayush Bandari, now at Imperial College London. But also one of his students and his former PhD advisor. So I don't document the work. So the main motivation that got us starting on this topic was high dynamic range imaging. We're not quite there yet to do imaging, but we are at least starting with high dynamic range sensing. And the reason why you do this is manifold, because you have sensor saturation problems in a number of different areas. One of the prime example that is often mentioned is for autonomous driving. When there is a sensor, it has to deal with very bright light outside, but also when the car is entering a tunnel, there may be sudden changes from an almost dark environment to car driving in the opposite direction and emitting a lot of light. So that's why you would ideally like analog to digital converters and sensors that can adapt and deal with a wider range of dynamic ranges or signal amplitudes for that matter. And we were looking a little bit into how this is done. So with like one of the key ingredients that I will use or propose for this is so-called self-reset ADC. I will say more what that is, but then I will basically tell you about two different recovery methods. So the first one that got us started, the algorithm, which is the most general, but somehow tied to like a little bit more ideal setup. And then tell you a little bit of how we have proceeded to see how these things can translate to practice and what can change if you do it with the real hardware prototype. But let's start first with the basics. And at the core of everything that I will be talking about is the analog to digital converter. And as you know, it's not only at the core of my theory here, but it's the core of a wide variety of devices that everyone is using. And I'm sure that most of the people in the audience have spent a lot of classes in their undergraduate education learning about how these things work. In particular, what you will have encountered and what is really at the heart of all this is the so-called Shannon sampling theorem, attributed to a number of different people, which basically says that if you have a signal that has bandwidth omega, then you can sample, you need to sample at a rate of at least 1 over emma, 1 over omega, and then you can reconstruct the signal exactly via a low-pass current. So that's the starting point, and that seems a very simple object here. You take like extracting signal value seems very simple. A low-pass kernel is something a low-pass filter is something rather simple. So what's the problem? And the problem, I think, as many of you know, is that in fact this very simple operation of extracting the value of a signal at a given point is not that simple in practice, because what will happen is that you will calibrate your analog to digital converter to a certain dynamic range, and if you exceed that dynamic range, the ADC will just output the maximum value. So here this is depicted in terms of the transfer functions. So the x-axis is the incoming value of the analog signal, and the y-axis is the output value of the ADC. And ideally, you would like to have a straight line like the blue one. The output should be exactly the input value at the given sampling time. But what happens is that for the calibration regime of the ADC, this works very well. But as soon as you exceed the dynamic range, the subsequent change is no longer captured, and you're getting just this output value. So what the consequence of this is that in fact we are not sampling the red curve in the picture below, which we would like to, but we're sampling the black curve, which is somehow cut. That's sort of the what a lot of people have probably seen before, and it relates to a lot of phenomena like clipping artifacts and so on that really come from this behavior. And this is also something that one encounters in imaging, as I already mentioned in the very beginning. So here it's illustrated if you're looking outside and you see this very beautiful sky and this church, the camera has to decide, is it going to calibrate the dynamic range to focus on the church so that the church is well depicted, or does it want to show the sky and with all its brightness potential? And this is sort of the classical camera. There are, of course, recent developments like high dynamic range imaging, which is now even included in cell phones, with proposing the approach that's based on fusion, where you take multiple images at different exposures and you somehow fuse them to an image like what we have on the right-hand side, that basically has one exposure for the sky and one exposure for the church, and then putting them together to create this image that you see here. This is one of the strategies here. The first one, image fusion, but there's also other strategies, interpolation, in-painting, and there are also some convex optimization methods have been proposed to get rid of this clipping. The important thing to note is that these approaches are entirely computational in nature. So we are taking this saturation and artifact as given, and we are then trying to revert it at the end when the signal has reached the computer or something like this. And what we are proposing, or what Gala started to think, is saying it's interesting that you have two objects that are in interplay. You have the hardware and you have the software, and then you're pushing a lot to change the software and to get state-of-the-art software, and you're still using the same hardware as before. And that's why we started looking and thinking, what do we actually want, and maybe trying to rethink what would be a hardware that could be an alternative. And one of the things that will be at the core of this talk is this so-called modulo nonlinearity. So here, this blue thing, this blue curve on the bottom, is what we have seen before as the transfer function of the traditional ADC. And now what we are proposing, or what we want to consider, is that whenever we're reaching this dynamic range threshold, we're proposing to reset the ADC to this other value, and then basically so that the subsequent change after this point can still be captured. That said, of course, we're losing at the other end because we have done these resets and losing some of these that information. It's by no means unique what we get here, but the idea is to sort of say, okay, if that one way of losing information can lead to problems, maybe a different way of losing information can be more favorable. And so basically, in terms of the transfer function, this means that whenever the signal reaches a certain threshold, it's reset to the respective other end, and so on and so forth. So of course, this is something talk is called From Theory to Practice. I could, of course, say, yes, it's nice that a mathematician can think about all these great things, what he would like an ADC to do, but something along these lines had actually already been proposed when we started working. Something, let's say related, because it's something that has been called self-reset ADC, also folding ADC. I think it's in the context of biomedical sensing. And of course, the question is, this is sort of exactly the picture on the upper left, is giving this modulo information, which really corresponds to the transfer function that I've shown you on the previous slide. So if you look at this, you can see that these hard jumps were given by these transitions here, hard from black to white. But of course, what wasn't clear, people have built these circuits, but they didn't know what to do with this information. So what they did instead, what I did in addition, they measured the so-called reset count. So for every location, it's not only captured what the value is of this modulo operation, but it's also captured how often the ADC has been reset at this particular point. And that's the second plot. And then, of course, I think that's not very difficult to see that if you can just add these two up and you get the original signal back. So in some sense, we have yes, we have increased the dynamic range, and it's preferred to a number of situations, but in terms of resolution, we have bits here and bits here, and so in the end, somehow we could just say we're having putting these two things together just has a higher resolution in the first place. So so it's just one way to make maybe an ADC with more bits or something like this. And so what we are looking at instead is, do we actually need this reset count? Can we recover the signal without this? So just from this first picture or the corresponding one-dimensional objects in the sense that we were discussing. That has, of course, some advantages. It reduces the storage costs, like sort of the precision here with the double information, both in terms of acquiring, like you need to sort of precisely capture when the jumps happen and so on, and also in terms of just the number of information. The idea here is that if let's look at this in an inverse problem. So we have, let's assume that the first thing is given. What can we say about the object of the function? And here, this is a depiction of how this can look like. You have this blue curve, which is our general oscillation. Here, this is the signal that we're interested in capturing. And now after the reset, so we've seen this black curve, whenever it reaches this threshold of lambda, it's reset to this lower threshold, then it captures. That's really just a folding operation here. And if you look at the black curve, visually, it seems, I mean, at least I would feel that it seems indeed easier to reconstruct the blue curve from the black curve as compared from the clipped curve. Like if I just, because here I can just take this object and sort of move it up visually and tie it to here, and then I get until I have a smooth curve. But that's of course only half of the truth, because we don't have the black curve, we only have the red samples. And especially here on the region on the left, if you imagine the black curve is not there and you only have these samples, I think that then it's again very difficult also visually to somehow complete the picture. So nevertheless, looking at the black curve somehow tells us that maybe there is hope that the situation is a little bit simpler than the other situation. But of course, that's something to be recovered. It's not clear in the first place. One would have to see, is it actually uniquely determined? Can one recover? There's a number of questions that we will have addressed in a number of works, or will address also in this talk. So let's start with our first recovery method. When we started working on this, we were looking at the following setup. So we're looking at a signal in one dimension that's bandlimited. So we have the frequency support is between, here say, -1/2 and +1/2, and we consider equispaced samples. And this is gamma k here. Gamma k, we should remember, are the samples of the true function. And then now we are having the self-reset operation. So we wanted to do a modulo. The modulo would be what one traditionally would think of as the modulo is this double bracket here, where you take the take the value and reconstruct its floor, which is somehow the fractional part. But what on the one hand we need to rescale it because we don't want to have the things modulo 1, but the other thing is we also want to center it. So that's why we add 1/2 inside and we subtract 1/2 outside. So we have it centered around 0 and not from 0 to 2 lambda. So if we look at it, however, it is true that this object that we've defined, m lambda of t, is congruent to t modulo 2 lambda, just as we wanted it. And this is what we assume that we have. This is our modulo samples. We call them yk. Let's recap, because this notation will come a number of times during the talk. So the gamma k is true samples, and the yk denotes the modulo samples, and g is the continuous function that we are having before sampling. So I will recall also later when it comes back, but I think this is something that helps to keep in mind. So now we want to use these samples. And so what's the basic trick that we want to do? So we want to use and work with the finite difference operation. And the reason why we want to do this is that a finite difference operation can make a signal small. And that again, in turn, can help because if a signal is small, then the modulo operation has no effect. So let's try to make this rigorous. So the reason here for this first lemma that basically says that the finite difference operation in nth order applied to these are the true samples of the true signal gamma, that it behaves like t like some constant to the n. So then we will argue that this constant can be less than 1, so that's exponentially decaying in the order times the magnitude of our signal, and that is really resulting from the fact that the finite difference is somehow closely related to the derivative. And so if it's if we have the nth derivative, then we're sort of approximating the function better and better. And that's why we get this exponential decay. So, but that is only, again, so it's some results about the finite differences of the true samples, and that's something that we will never have, because we're starting with modulo samples. We only have access to the modulo samples. So, and we cannot tell the system to do a finite difference before. So we have to still need an additional ingredient, and that's the following commutativity relation. Because what we see here, if this is sort of what I said, we could have potential control over the modulo operation applied to the finite difference of something. And we don't have this, but it's what we see is that it's the same as the modulo operation to apply to the finite difference of the modulo information. So which basically, this is something that we have access to. So if we want the thing on the left, that's something that we can compute by just taking our modulo samples, applying the finite difference operator to them, and then applying, like, sort of computationally applying another modulo operation. Okay, so that's what we have here in terms of gamma, the true samples and the modulo samples. It means that the finite difference, having the modulo operation applied to the finite difference of the true samples or the modulo samples doesn't make any difference. And so, which basically tells us that we have a computational way to get this modulo operation of the finite difference of the true samples. So how does this help? And I think basically that's the lemma that I've just shown you up there, because if we have this something that the lemma allows us to control and make it very, very small, and if we make it smaller than lambda, then m lambda has no effect, and then we have the finite. So we, from the modulo operations, we get the finite difference of the true samples. Okay, so that's where we stand. So we said this is small, and now let me just try to write this down, what I just said. Here we said that the finite difference of the true samples is equal to the finite difference of the modulo samples, equal to the modulo operation of the finite difference of the modulo samples. So we base this, the right hand side is something that we can compute because y is what we observe. So which basically allows us to also get the left hand side. And then this tells you, I mean, we said we want this to be less than lambda, so we have to be a little, we can compute exactly how many finite differences we have to choose. And you see that this depends on the amplitude of the signal. Nevertheless, we call our method unlimited sampling because it's important to see what we need is that the sampling rate t multiplied by pi times e is less than 1. And this is something that can be achieved by an oversampling rate of something like maybe 2 times pi times e, so which is a constant, which means the circuit that we need to encode our things doesn't depend on this information. So the way we sample is really in that sense unlimited in that it doesn't require any information. The n, this n here is only used in the reconstruction. Okay, so there's this on the first glance may seem promising, but there's still, of course, some very, very difficult bottlenecks to overcome, because having a finite difference is certainly typically not enough to say anything meaningful about the true signal, because the finite difference is like inverting a finite difference is very, very unstable and also ill-defined, because in every step, it's like if I invert a first order finite difference, then I can do this. This is some type of integration, so then I can do this up to a constant. If I do it twice, then I can do it only up to a linear function, then a quadratic function, and as soon as n goes up, then you get some type of polynomial where you of course have no idea how this looks like and how you can get rid of it. So that's why it may seem that we have done an academic exercise that is of limited relevance here. But the point is that we still have access to the modulo samples, and that is something that we will exploit. The way we do this is the following. So let's look at what we call the residue epsilon gamma, which is, recall, gamma is the true sample, y is the modulo samples. If we take the difference, we will get something like the residue. And just by definition, so thinking of that, we have defined it via the fractional part and so on. The modulo operation, what the modulo operation does is it subtracts some multiple of 2 times lambda. And for that reason, this epsilon gamma will have values that only lie on this grid 2 lambda times c. So if we, at the same time, we have access to epsilon, like so epsilon or recovering epsilon gamma is equivalent to recovering gamma, because y we have, so we can just add epsilon gamma plus y and get gamma. And I argue that this is very good news, because epsilon gamma does not have a number of the problems that we were discussing before. Namely, it lies on this grid, which makes the finite difference much easier to invert. How do we do that? So we have the nth order finite difference, like we just say, we start and iteratively reduce the order of the finite difference operation. So let's start with the very first step, delta n, what we started, delta n epsilon gamma is what we have. How do we find delta n minus 1 epsilon gamma? And of course, now we have the problem that I mentioned, that it's not even possible to say this uniquely, because if I invert this, I can only do this as up to a constant. So I can, and the way how I invert it, I do these partial sums. So I'm summing up all the elements from the first to the kth, or the ith in this context here, and that sequence is then a potential inverse of the finite difference. So, and as I mentioned, this is the solution up to a constant. And this is really where it helps to consider epsilon gamma, because this time now it's not an arbitrary constant, but it's a multiple of 2 times lambda. And that is to say, if we do it again, then we get another constant, again, a multiple of 2 times lambda. But this constant here is integrated once more. And now we have something that is increasing very quickly. It's like from 2 lambda, 4 lambda, 6 lambda. So it has a predefined growth. And then we can use the fact that we know that our object that we're looking for cannot be arbitrarily large, right? So we have some tight control on how large the infinity norm is. And so if we choose the wrong constant here, this will grow very fast. And in a well-controlled time interval, we will exceed the range that is admitted. So we can play around with exactly this observation and get an explicit expression how to compute this kappa. and then we just proceed and go up one finite difference at a time, noting that the last constant ambiguity cannot be resolved. And that's natural, because if we add 2 lambda to the full signal, it gives rise to this exact same modulo sample. So there's no way we can resolve this. And the trick is, I mean, I've already mentioned in terms of the constant that it's useful to integrate, to work on this grid. It's also in terms of stability, because if you know that all the different iterates need to lie on this grid of size 2 times lambda, then in every step we can compensate for numerical errors by rounding to that grid, which means that the whole method is more stable. So this is it. I mean, I'm not going over it. It's just following exactly the approach that I've just designed here with this finite difference, computing this kappa. And then in the end, one thing that I haven't said is, of course, if you want to get your approximation to the band limited signal that you're looking for, you need to still do the low pass filter, because what we recovered was the true samples. And this theorem here, also just summarizing basically what we have done here, is saying that this works provided this oversampling rate is larger than pi times e, which is about 10. So I think at least if we want to have a little bit more stability here, then let's do 20, and then everything works well. Okay, so let's see how this does numerically. This is the method, and for a randomly generated band limited function, and you can see that lambda is fairly small as compared to the amplitude, and from this red data, I think I would find it difficult to sort of complete it visually, especially here in the middle. But our method, it's sort of visually and also in terms of machine precision and exact solution. Okay, so there's that. Now we have, I mean, I should mention there have been some extensions on sparse sums of exponentials, sparse sinus empty mixtures. And the idea that's coming next is sort of to try these techniques or this viewpoint and maybe combine with some other approaches related to finite rate of information, Crony's method, and so on. But that is something that, I mean, this is something that's here is already, we have used some type of Crony method, and that will come again in the second part of the talk. And here in this context, we should say this only needs finitely many samples. Okay. So this was a first overview of where we stand. And now then, of course, we have done all this theory. And now let's try to see, does it work? Or of course, we want to somehow build. And that is what we have done with one of Ayush's undergrad students, actually, Tom Poskett, who I also mentioned in the beginning. We put these things on a circuit board, basically having a hardware prototype that can then be connected to an oscilloscope. So, and I will show you how this looks like to just see what we have built. Go this. I hope you can all see this. So you see, we're driving up the amplitude of the signal. So that means we're having more folds. And then we're driving down the amplitude of the sinusoidal signal here. And then basically the modulo has no effect. And so, of course, you can see the more, the larger discrepancy between the amplitude and the cutoff threshold, the more folds you get. Okay, so that is sort of the visual demonstration in terms of video. Let's move back to the presentation. This is what I did, the video demonstration. Now let's have a first glance of looking at how this works. So what we did is that we just summarize this, generate some band-limited signal. In the previous picture, I've shown you that we generated some type of sine wave, and now what we're doing here is some type of band-limited signal. And then we apply a modulo operation in this analog domain as implemented via our hardware prototype that I've shown you. And so then we connect it to an oscilloscope, and then what you see is this. So what I should mention is, and this is why we use this particular setup as the first way to compare these things. We want to somehow compare, so we want to see how our method helps, and that's basically we are interested in the case where the signal exceeds the dynamic range. And so that is the case here. The black signal exceeds the dynamic range of this sensor, of this ADCs of the oscilloscope, and this, but the oscilloscope has an automatic gain control. So it rescales this black curve to the level that we see here, and the red curve, because we have our analog hardware prototype before it, doesn't need to be rescaled, and that's why they don't match even in the regions where there's no reset. So you can see that, but you can, I think, imagine that if you scale the red curve down or the black curve up, then they would at least in parts be aligned. And this is something what we have done here on the right. So we have done this rescaling, reversed this rescaling, and put the curves on top of each other. And you see, yes, this red curve has the jumps that are coming from these folds. Naturally, that's what we built. But in the regions where it matches, the red curve is much smoother. And that's not surprising, because the automatic gain control has naturally led to reduced accuracy on the fine level, reduced resolution on the fine level. And that's what you can see here. The black curve is much rougher. And if we take this red curve now and reconstruct using our method, then you can see that we really get something that is on top of what we would like to see and looks more like the signal that we expect. Okay, that was the first glance. And yes, I could stop my talk here and say we're finished. But of course, if we're looking a little bit more closely, we also see some rare artifacts. And so occasionally things can also go wrong. And the question, how this looks, you can see here. I mean, this is what we've plotted here. Also some band-limited functions, some example. And as you see here, especially, then these the folds here, the black is the sort of the residue from subtracting them, and so you see that there's a few here and here that are not exactly on the modulo grid. So, and that in the consequence, if you're taking finite differences, that means that we're having also a few of the finite differences that are somewhat in the middle between, that don't have the value of 2 lambda or negative 2 lambda. So why should this be the case? I mean, the reason, there's many reasons that one could think of, but one reason is that in our theory, we always assumed an instantaneous transition from both ends of the modulo spectrum. And that is something that is not the case in practice, right? So you have some type of a very, very short transient. And if you have a sample that lies exactly on the transient, then that is rare. And you don't see it very often, as we've seen on the previous example. that didn't happen at all. But it can happen, and then it can throw our method off. So that's why we're thinking of, is there a way we can be a little bit more robust to this? Because like part of the reason is what was the method that we've seen before, sort of explicitly used in this commutativity relation that I showed you, explicitly used that the signal is on the resets are all on this grid of size 2 lambda. And so let's study a slightly generalized model. First, it remains that our function g is band limited. And in addition, we are a little bit more restrictive in the model. In the sense that we assume, in addition, some periodicity. So we are, that's previously we had band limited, now we have periodic. And which basically says that our signal is some type of a Fourier series coefficient, which is whose Fourier series coefficients vanish beyond a certain value. And then, but at the same time, we have sort of a slightly more restrictive model, but we have a more general model for the modulo nonlinearity. So what we assume is that it's no longer, we assume that it subtracts a piecewise constant function that lies on the grid, but we say that it subtracts an unknown piecewise constant function with arbitrary values. So here, that basically we have this generalized modulo linearity, the generalized residue, and there's no assumptions that this residue has certain values. But at the same time, of course, it's allowed to lie on the grid. So this aspect is backwards compatible with what we have seen before. So then again, we're having k equidistant points. That means we have t is tau over k in this context here. And we have a relationship of, in analogy, what we've seen before. We again call gamma the true samples, so g of kt. Then y is, in this case, the modified, the non-ideal modulo samples and tilde of this object. And then r is this residue that we defined, that we have seen before, which we assumed is piecewise constant. And that's what we want to exploit now. So the recovery idea here is we have a piecewise constant. So our modulo, generalized or non-ideal modulo samples that we observe are the sum of the sampled band limited signal gamma, okay, the true samples that we're looking for, and the piecewise constant. I mean, we sort of have to shuffle things around. That's why things get a minus. And so the idea, I mean, we have taken a lot of finite differences. Here we've taken just one, but that helps because if we have a piecewise constant sequence and we're taking finite differences, then what we're getting is a sequence that just has a finite number of spikes. So why is this useful? Because when we go to the Fourier domain, we can say more about what the different things entail. If we have, I mean, the sample, the band limited part, and we go to the Fourier domain. I mean, that's what band limited means. That's what we can see here. The band limited part in the Fourier domain will just live in this very restricted compact interval related to the bandwidth. And on the other hand, if we have just a small number of spikes and we move to the Fourier domain, then what we get is a nice trigonometric polynomial. So here, band limited part goes to compactly supported, and the spikes delta r go to some trigonometric polynomial. And so in particular, if we look at this picture here, outside of this bandwidth, here we have this region here. In this part, the trigonometric polynomial and the band limited part overlap. basically we can't say very much. But in this region outside of the bandwidth, we only have this trigonometric polynomial. And there are a lot of methods along the lines of Prony's method, for example, what we used in the experiments is matrix pencil, but there's many others that allow to recover a trigonometric polynomial from some reduced set of equispaced samples, in this case here, in this regime. And so basically, even though we don't have information in this black region, because it's sort of overlaid by the unknown band limited part, it allows us to reconstruct R. And once we have reconstructed R, we can also then, of course, get the signal back. Okay. So the result, like I hope that the method has become clear. Let me show you the results. So we have T periodic, and now we have a different type of assumption than before. Basically, we have some restriction on the number of folds that we have in the interval. That's what we need for this Prony type method. And then we need to make sure that the samples are somehow enough to capture the folds. But once we ensure this, then our Fourier-Prony algorithm, along the lines of what I've just described, recovers the samples from the modular samples. It's generalized without knowing exactly how what the values are of this m lambda tilde operator. Okay, let's revisit to this example that I've shown you here, this sort of artifact example where we had these jumps that were sort of non-ideal here. The left-hand side, I think you have seen before on the previous slide. Now let's apply the reconstruction. And as you can see, just because these artifacts, they don't really match what I've told you in the first half of the talk. That is, if you have this dashed line here, if you apply our method that I've told you, then exactly at these points where these strange things happen, we have some mismatch. So you see that our method is off in these points, whereas the method that I have just shown you here, this giving rise to this red curve, indeed gives you a correct reconstruction. Let me sum up. So we have seen two algorithms. So like one is what we call the unlimited sampling algorithm, which sort of has the caveat of assuming an ideal modulo nonlinearity, but it's more general in that it works for arbitrary band limited signals, has no restrictions on the number of folds. And I argued to you that this ADC in this context is unlimited in that T doesn't depend on G. On the other hand, the Fourier-Prony approach, it has the distinct advantage that it can work for non-ideal modular nonlinearities, but it currently still is restricted to the periodic setup and requires a bound on the number of the folds. At the same time, it's less restrictive. I mean, I haven't had time to show you, but you can see that it's less restrictive on the oversampling requirement than the previous approach. So that that said, of course, there's a lot of things that are still open or potentially interesting. First of all, we have seen something on incorporating these non-idealities when the signal is not periodic. And what, like when it's periodic, what if we don't have this with a more general setup? What if the cutoff threshold is not exactly? Can we need for the recovery, we somehow need an information on the amplitude. Can we somehow estimate this from these modulo settings? And then, of course, if you want to go ahead and apply this with other signal processing techniques that are other ways of sensing where you have additional structures, information like compressed sensing or a learning of various types. That of course would also be very interesting. But with that, I would like to thank you for your attention and of course welcome any questions that you may have.
Thank you, Felix, for this excellent talk. Very interesting. So we have a couple of questions here in the chat. So there's the first question by Malte Schellmann. He's asking, where can I see the remaining ambiguity in the reconstructed signal on page 19? So it's a particular question on page 19.
Okay.
So where can I see? Yeah.
Yes. Okay. You think, okay, the remaining ambiguity of lambda is, I think what we have done here is that we've sort of, among the solutions, we have taken the one with smallest energy or something, which is, but you're right that typically, technically, I could also draw a solution that's completely up here, and that would sort of be a valid solution. Yes, but the very, very good point.
Okay, thank you. So there's another question by Florian Ruemer. Florian, do you want to formulate this? Yeah.
Sure. I hope you can hear me. So first of all, very nice and impressive talk. I have to admit I've been following this work on unlimited sampling for quite some time, and I have to admit I was always skeptical whether it's going to work in practice, even though I was fascinated by the theory. It's very impressive to see that you actually built it. I have a question regarding the hardware prototype that you built. I mean, I know it's a prototype, but I was wondering how fast it can actually be made, because the transition is probably taking some time, the self-reset. And if the signal changes rapidly during the self-reset, I'm not sure what works. So how fast is this? So what bandwidth of signals can actually be supported by this implementation or by potentially others that could be made?
Okay. So this is an excellent question. I mean, I can't give you I would have to see, because as I said, the caveat of another caveat of the pandemic is that I haven't sort of been the hardware development is happening at Imperial, and I haven't been there for a very long time.
Yeah.
So, but I mean, I can certainly find out these facts for you. But let me just turn the question around, because I think this is an excellent question. What we are currently working on, and what we at least would find very interesting is, or at least the approach is again very much in the spirit of computational sensing. Is yes, we can try to we have our model, and let's try to fit our hardware to really meet our preconceived model. But at the same time, what I find the more promising approach is to say, okay, if this is the hardware we want to build, in the end, like I can invest a lot of time to make these transitions very, very fast. And then this will be an extremely expensive circuit, and nobody would like to have it, right? What I think is the more promising approach is to say, let's just admit that there is a certain transient. And also there's some other hardware effects that we still want to, that we still in the process of identifying. That's one of the main purpose that we had for building these prototypes, and then say, okay, we could try to sort of use advanced circuitry in order to sort of reduce these effects as much as possible. Or we can say we have, it's the great power that it's intertwined between hardware and software. We could also try to see, let's take the hardware as it is, because if it has transition, it's still capturing some information. And sometimes having a sample on the transition gives you even more information, because it allows you, I think we have an ICAST paper where we sort of have some steps in this direction. I think it was last year or something, where we're still working on the journal version, where saying like that it's in fact great if you have a signal a sample on the transition, then like if you have a transition and you don't have a sample on the transition, then you know that the transition is somewhere in between and you don't know where. And at the same time, if you have a sample on the transition and you're correctly identifying it, you can exactly locate the and you know how fast your transition is, you can exactly locate the transition. And in some sense, I mean, we're by far not there yet, but that is, I think, I would say, I welcome the question very much because I would like to sort of argue that this is the way to go. And rather than trying to say, ooh, are we there yet? Can we maybe make it a little bit better? Because as I said, and I think that the main point, I think that Ayush was saying that he's very proud of his student, that our hardware prototype is built from off-the-shelf components. So it doesn't need any sort of advanced made-to-order components. And I think that's really a key to success in the end, as I was saying earlier. So if, like, part of the thing is that, yes, I was saying, if we have the reset count information and if we have the modulo information and we can put it together, and then we have when we have, say, now we have 12 bits on the reset count information and 12 bits on the modulo information, then we should compare to 24-bit ADC that we had in the first place, and then maybe the advantage will not be so great anymore. So in the end, if you want to make things very costly and very precise, if you have to, then maybe that's you're sort of giving away some of the advantage that we set out to create.
Yeah, I agree with you. Maybe just I was wondering more about the order of magnitude. So are we talking kilohertz or megahertz or gigahertz here? I mean, what are you targeting as what types of signals are you targeting? Because
okay, that's a very, very good question. So I don't.
It's okay. We can take it offline.
I will. I think. Let me see what. Yeah. Okay. I think I will connect with you offline.
Thank you.
And
thank you very much. So we have another question by Ken Ma. He's also here. Yeah.
Okay. So can you hear me?
yeah.
Right. I guess my questions are quite general. Have you tested your method in the presence of noise? How sensitive to noise or perhaps modeling error and uncertainties?
Yes. So I mean, in some sense, what I've just shown you is a presence of modeling error, right? At least the last part of the talk, it was geared to exactly to this. So there's two answers. The first thing is that, I mean, I didn't present to you because it would have been more complicated. We have theory that ensures robustness with respect to bounded noise, in particular quantization noise and stuff like this. So in the first setup that we have, that it's theoretical and it's also sort of confirmed in practice. It's
slightly more curious. So when you use bounded noise, you don't assume Gaussian or statistical things. You look at the worst case.
The point is, again, yes, we currently don't assume this. And the point is that one would need, I mean, I know that some people have sort of, I mean, I know that sort of in parallel to us starting these approaches, some people have worked on noise removal for these modulo samples. So basically that you have denoised modulo samples that you're doing. The method, I mean, I'm not sure about the second method. So that's it. I think that's something that we definitely have on our agenda. The point is the first method as such will be, can be rather, say if you have very large outliers, but if you have Gaussian noise, then this includes some very large outliers. And if you, which basically means that probably, it means that some sample is more or less deleted. Because if you if it sort of exceeds a certain range, it just behaves like uniform random and basically has no information anymore. And so the point is, because we're having this recurrence relation, so we can just introduce some spurious folds resulting from these extreme outliers. And that then so basically we have a correct reconstruction here, and then we have some fold, and then we have another correct reconstruction here. And so this is sort of what we have to tackle if we want to sort of go really with this unbounded noise models.
Mm-hmm.
At the same time, and that's, I think, also one of the big insights coming from the hardware prototype, is that apparently the noise in our implementation is smaller than we expected. So as I said, it seems to be that these hardware artifacts are coming from exactly the phenomena that we've discussed. They are playing a much more significant role than just Gaussian noise or sort of that type of perturbation, in what we observe. And I think I agree with you that it's important to have a complete theory to also be able to tackle this, but we were surprised, we were sort of driven by the hardware experiments to see where we should our first focus on. And that was here, this type of artifacts that we've seen before, because they visually appeared, whereas sort of probably there is some very small noise, but at least it was not causing substantial problems. So if you at the same time, if you have sort of individual, like, so I'm not sure, but I assume that the second method could also be able to potentially be dealt with, because if you have one outlier that's somewhere, then you can also think of it somehow as just some piecewise constant part that's sitting there somewhere. Maybe that can also do it. I think we have run some experiment, but we haven't sort of theoretically investigated what works and what doesn't work. So, but I think that it's definitely on our agenda, if in particular, because as I mentioned, and I think I have some student who will be starting just next month, if we want to go to imaging and we want to do two-dimensional stuff, and then of course these things play more of a role.
Mm-hmm. All right, so I hope you won't mind if I ask one more question. I try to be swift and more general. Are there any interactions between this modulo sampling and sigma delta?
That's also a very interesting question. It's something that I have also thought about, because I have also made a number of contributions to sigma delta and so on. And the first answer is, we have a paper, and I think my student Olga received an ICASP Best Paper Award for this a couple of years ago, where we design a sigma delta approach for these unlimited samples. But so basically we can do this with sigma delta. But I think maybe what you were addressing was slightly different in focus, in the sense that it is because we have these finite differences, and a lot of things there seems to be some analogy of some sort between sigma delta and this. Exactly. By the way, we control stability in sigma delta and here. And so I see this, and I also have been thinking along the way, but I think that I have some ideas where this could be made more formal, but I think that's not at any point yet where I could say something concrete. But I think I know exactly where you're coming from.
Yeah, I know. Yeah, thank you very much. And I forgot to mention that it's really interesting talk.
Thank you.
Thank you very much, Ken. So we have another question by Malte Schellmann.
Yes, thank you. Actually, you have already partially addressed it in your previous answers. I wanted to know, about the maturity of this technology. You know, in communication engineering, we still spend quite a lot of effort on designing waveforms with a low peak to average power ratio, and the reason is due to these ADCs with the saturation range. So we want to stay in the saturation range. So this technology would allow us to go one step further and kind of to overcome this PRPR issue. So it's highly interesting, of course, for communication engineering. But I would like to know, what do you think is the maturity of the technology, and what do you think when it will be able to be applied in communication systems? Do you have any guess or any idea on that?
That's a good question. So it's hard to say. As I said, as you've seen, I mean, even the publications, the TSP papers, they are just, one has just been accepted, one is just this year. So this is, in that sense, also from the theory level, it's very recent. So it's really I think what would be really interesting is, maybe for this communication. So what is technology? I think it's I've been talking to some people about this particular application a while ago, but it's, I find it very difficult. I would say it probably still needs a little bit of time, but it's difficult for me to judge what's the number of years that we should. Because as we said, like, I think there's a lot of development in the sense that some people seem to be interested in picking these ideas up. But so at least to what I know, there is not, so that the connect between hardware and software is not there yet in many areas. So in the sense that there are some people working on the hardware front to sort of design modulo sensors or similar objects, and then there's some people doing more computational things, but sort of I think this paper that I've presented to you was one of the first where we're sort of really trying to do the connection. And so it's very difficult to say, and especially this question will play an important role that were just asked. So we have to sort of look at the specific implementation to see what are the artifacts, what are the errors that one is encountering in that particular scenario. And then the question is, can we find and can we address them using these computational methods that we have, or do we need new tools? And that I think will also play an important role that I cannot judge at this point.
Okay, yeah, thanks a lot.
Thank you very much. We have time for further questions. There is Florian Ruemer again.
Right, just trying to start my microphone. Okay, I was wondering about the dynamic range, because we do actually have some sensing problems where we have very weak signals that are buried under very strong signals. And the difference between their amplitude can be 30 dB, it can be worse, it can be 40, even 50 dB if we're very unlucky. So typically to solve this with classical ADCs requires very, very high precision, which is a problem. Now, the examples that you were showing more suggested that the dynamic range factor is not that high. I'm wondering if there are any fundamental limits or if it can even go to several orders of magnitude. What's your...
So I think that, let me just go to the, let me just go here to the result. Like in the first part, there is, so let me try to recall where this is. So in some sense, so what we are drawing, so the question is really how to deal with, like, one thing that's playing a role there is how to deal with stability. And the point is that what I tried to argue in the first part of the talk is that we're having this stability advantage coming from the fact that our finite differences and also the signals are on this grid of size 2 lambda. And the the larger this dynamic range like differences, the less distinct this advantage becomes. Because if I say at some point, if it's sort of this quotient is sort of too large, then it's just a regular round-off error. So I don't gain very much, and I don't gain a lot of stability here. At the same time, and we have another leverage point. So that's why sort of having like a fourth, fifth, sixth order finite difference may be unstable and difficult to invert. At the same time, we also have the oversampling rate as our parameter. That's something that we haven't really focused a lot on exploring. But if you are having, so basically this is what makes the things sort of theoretically unlimited, is that we can sample at a fixed rate and then drive up this parameter n, but at the cost of potential instability. And at the same time, if you are willing to sort of oversample by a larger factor and investing in this constant t here, then we can reduce, we can have a smaller number of finite differences orders. And so if you have fewer finite difference orders, then I expect that it will be easier to invert. But so it will be more stable, because the stability of course builds up, problems of course build up with the implementation. And so that is something that I can't answer off the top of my head, but it's a very interesting thing to explore. And of course it's very nice to see that these problems are of relevance, and that there is interest in the general direction.
Yeah, thank you.
Okay, thank you very much, Florian. Are there further questions? So currently I don't see any further question. So if there are no further questions, I would like to conclude this seminar. I thank you, Felix, for this excellent talk. And I would like to thank all of you in the audience for your participation. I would like to remind you that next week we will have a seminar at the same time by Professor Thomas Schön from Uppsala University, and he will speak about deep probabilistic regression. So I hope to see you back here next week for this talk. Thank you all, and goodbye.